Okay, so this is shear example 4, and that's going to be continued. So in step 2 we talked about how we would calculate the stress acting at the centroid, or at the neutral axis, and we reminded ourselves that we are using that everything is being measured relative to the neutral axis. So then the next bit of the calculation would be calculate the maximum, calculate the shear stress in the weld. So let's just draw this out here. So we've got this neutral axis is there. So we've got the web there, or the flange, and then we've got the two webs coming down. So I'm not going to be drawing the other half of the beam below the neutral axis. So in this bit here, we're saying we're going to be making a cut, and we are wanting to work out the stresses or the forces on the weld in the direction in plane, in the direction into the sheet of paper. So let's imagine that we're making a cut here. So we now want to work out. Let's say we want to work out the stress. So we'll have method 1. So method 1 is based on calculating the stresses. So we'll have V S dash divided by I B as a function of Y, and in this case here we would, if we drew the Y up there, the value of the Y which takes us up there is going to be 560 divided by 2. So 560 divided by 2 is going to turn out to be 280. So we've got a value of Y where we want to make the cut, and that's going to be at 280 millimeters. So B as a function of Y is 280 millimeters. So okay, let's just say tau at 280 millimeters is going to give us a stress. So the I, nothing has changed. The I is going to be 1.361 times 10 to the 9 millimeters to the 4th. Nothing has changed. Our V is going to be 1750 kilonewtons. Our B is going to be the breadth at 280 millimeters up, measured up. So since we're talking about stresses, it's going to again be our T2 plus T2. So that value there is going to be 24 millimeters. And then all we need to do is to calculate this value S dash at 280, and that's going to be that shaded area multiplied by the distance of the centroid at the shaded area. So the shaded area, so it's going to be multiplied by that distance down there. So the area of there is going to be equal to A, just call it A1, and A1 is going to have been 300 millimeters multiplied by 20 millimeters, and then the distance down, I suppose, is going to be 280 millimeters plus half of the top, which is going to be 10. So I suppose that's going to be 290 millimeters. Let me check. Alright, it's just 280 plus 10. So we're going to have our area, and that's going to be multiplied by the distance. So that's going to be A1 multiplied by the distance from the neutral axis to the centroid of A1, which I think is going to be 290 millimeters. So if you substituted all that, you would get a value of the stress. That value of the stress that would pop out is going to be, so the stress at 280 millimeters, that would have worked out to be 143.6 newtons per millimeter squared. Now, if we then multiplied the stress, if we then multiplied that stress by T2, so if we then multiplied that stress by T2, that is going to work out to be 93.23 newtons per millimeter squared. And then if we had multiplied 93.23, so that's going to be the stress there. So stress here. So 92.23. We multiply that by T2, where T2 is the thickness of 12 millimeters. So that's newtons per millimeter squared. We're going to get a value of 1.119 kilonewtons per millimeter, which is the and that is the the demand on each weld in units of kilonewtons per millimeter. So each of these two welds is that weld there and that weld there is going to need to take 1.19 kilonewtons per millimeter. Now there's another way of doing it. So method 2. So method 2 is going to use the other expression, which is the shear flow expression, and the shear flow expression is just Q is going to be equal to V multiplied by S dash divided by I. So you can see that your B in the denominator side has disappeared. So previous expression there was that B has now disappeared because that one is no longer a stress, it's a traction, and the units are kilonewtons per millimeter. So we've eliminated the bottom bit. So again, nothing changes. We'll now be working out the traction. That bit would also be at 280 millimeters, and then Q would also be calculated at 280 millimeters, or the shear flow would have been calculated at 250 millimeters. And then we would have said something like we would have worked that value out, and that value would have come out to be 2.23 kilonewtons per millimeter. So nothing has changed from the previous calculation in method 1, except that we don't have the B term. And then from there we would have said demand on each weld is therefore equal to 2.23 kilonewtons per millimeter divided by 2, which would then turn out to be 1.119 kilonewtons per millimeter. So hopefully you can see that this shear flow in kilonewtons per millimeter now it's not a stress anymore, it's a traction, and then that traction needs to be shared on each of the two welds, because on each of the two welds. So then we get the demand on each weld, again the same answer as 119 kilonewtons per millimeter. So now in the there was a table provided which shows the weld sizes, and we know that a weld of 1.119 kilonewton per millimeter needs to be found. So if we showed weld size, and we had 8 millimeters, and then we had the design capacity, and then the design capacity in kilonewtons per millimeter, and then we saw that for 8 it was 1.11. 1.11 is smaller than 1.119, therefore an 8 millimeter weld would not work, and if you designed an 8 millimeter weld, the weld would fail. And you can see that the 10 is 1.39 kilonewtons per millimeter. That is greater than 1.119 kilonewtons per millimeter. So you would then choose a weld size of 1.3 of 10 millimeters, because that exceeds the weld, that exceeds the demand on each weld of 1.119. So the answer to the question would be choose a weld size of 10 millimeters. So now after this I will go through the calculations in a bit more detail.